All right, so today's little video, we're going to talk about Poisson distribution some more. And from there, we're going to kind of branch off into our first, it'll be kind of our first introduction to a continuous that has a real name, not some phony one we've made up. So Poisson distribution talks about it is the number of occurrences of whatever in a period of time. The idea being is when we look at this, we want to know, in essence, how many of these items are happening. So in other words, we frequently saw something that looked a lot like this. You'd expect to see 3 per. Now, when I've done these and I'm done in my videos, I talked about, anytime I hear a rate, okay, well, technically it's supposed to be. Originally, when it came out, it was the Poisson was developed. It was always in regards to time. However, you can have them a little different than that as well. Like for instance, you get 3 potholes per mile or something, right? But you could have 3 idiotic conversations per day or per. No, let's see. Well, no, 3 idiotic questions per hour, when you're teaching high school, right? I mean, that's a pretty good rate right there. So if you think about this, well, how many should I get in 1 hour? Okay, well, this would be my expected value for the Poisson distribution, right? So I'd expect 3 of them per hour, right? Where this is t right here. So the idea is that mu is equal to, and then frequently they'll use, well, it depends on which book you're talking about. Some books will use K. Some books will use lambda. Frequently, they'll use lambda. And it'll be like this. Oh, fiddle faddle. What just happened? That's interesting. Your computer is low on memory. Oh, that's cute. Oh, all right. Huh! I'm going to keep rolling. I guess if it shuts off, it shuts off. What are you going to do, right? Sue me. Now, remember, this is idiotic questions per hour times hours. And you get 3 idiotic questions. You see that? Oh, look at that. That's cute. IQs. Nice. Yeah. So when you do this situation here, okay, that's great. But to go hand in hand with how many do I expect to get per hour, I can also look at it as how long should I wait per idiotic question, or how long should I wait? Do I have to wait? Do I have to wait? Per idiotic question, right? Between each idiotic question. Between each IQ, okay? That is a distance. Well, as soon as you think about that, well, how long? That's time. What does time look like to you? Well, time to me is continuous distribution, okay? And so this function has a name. This function is what's called the exponential distribution. Now, clearly, there's some ideas here. Well, first of all, it's a PDF, so duh. The integral of this PDF, right, has to equal 1 over its whole interval. Now, where would this interval start? Well, 0, because it's time, right? I mean, you have to have time. And where is it going to go to? Like, theoretically, infinity, right? Now, quite clearly, I would expect the probability that I have to wait, let's see, if I see 3 idiotic questions per hour, that's on average, you're thinking about, well, it's about 1 every 20 minutes, right? What a nice job, nice work, kid. So the idea that I'd have to wait more than 30 or 40 or 50 minutes is pretty slim. Are you with me? It's pretty slim. It would be that I have to wait like an hour between them, right? If I'm expecting it to be, 20 minutes. And the idea that I have to wait 7 hours between idiotic questions is not going to happen. Are you with me? It's not going to happen. And so 7 is not very close to infinity. So clearly, as you get to infinity, it's going to 0. I need a function that goes to 0 as I go to infinity. The only function that comes to mind is e to the negative x. Are you with me? That's the only function that I can think of right off the bat anyways that goes down to 0, yes? Now, and it gets there pretty quickly. Okay, and so this is why it's called the exponential function. And in fact, the exponential function is just e to the negative lambda t. Okay, now t obviously is my variable this time. T is the variable. Okay, now you recall on the I have to look up what your book does here in a second, as I've forgotten. This is f of t. Are you with me? It's a function of time. Now, the Poisson distribution, the way your book writes it out, now I never remember. I always have to look it up. I think your book uses lambda. I want to say it uses lambda. Oh, for God's sakes. Come on, Jay. You can do it. Probably, maybe. Oh, for the love of Pete. No. Yep, I lied. So your book uses this as well in the Poisson distribution. I don't really like it, but I just be aware that that's what it is. And so it's the P of, this is how your book writes it again, P of X is equal to, and then it is lambda t. This is how your book writes it. I don't really care for this, so I'm going to go ahead and just show it to you anyways. I like it this way only for one aspect. Okay, and then of course x is equal to 0, 1, 2, right? Now, typically most books will go, listen, lambda t is really just the expected value, or it's mu. So most books will write it this way. And this is why most people, when they learn it, don't understand the relationship between these two distributions. Okay? And so most books will write it as this to the this over this number. Okay? And nowhere in here do you see lambda t anywhere. Are you with me? So I will give your book that. That's kind of a neat way of doing it. Okay? Or whatever. Okay? What happened? Okay, so here we are at this point, juncture. You're looking at it, and you're like, okay, I guess I can buy your point of view, Jay. Well, what happens if x equals 0? Okay. What happens if I haven't seen anything happen yet? It's a good question. Let's take a look at this guy right here, shall we? Well, if x is 0, then you're going to end up with the probability of getting 0 events to happen, given that you expected this many. Remember, this is the expected value. Is equal to e to the minus lambda t. Of course, this piece here to the 0 power is 1, and obviously x 0 factorial is 1 as well. And you're like, well, that's interesting. So this is the probability of getting 0. That's right. Oh, well, that's interesting. Well, what's the probability that I get more than 0? Probability that I get greater than 0. Well, I don't know. Yeah, yes, I do. Probability I get 1 less than 0 is 1 minus the probability of getting 0. Yes? Right? What am I doing? That's what I meant to write. You see this? And so if I do that, well, what do I get? Well, then, wait. This is 1 minus this. That's cute. Well, wait a minute now. That's interesting. This, it's kind of weird because I feel like this guy here has a very cool property. I feel like if you evaluate this, so if you look at this thing for a second, just bear with me for a minute. Suppose I take the derivative of this guy with respect to t. Okay, for no apparent reason at this point, you're just like, oh, I'll play along, Jay. Fine, whatever. God, I feel like I do everything for you, Jay. That's right, you do. Wait, this guy right here, that's interesting. What is weird about this function? Check it out. What happens to this function if you integrate it from 0 to infinity dt? Turns out you get 1. It turns out that this piece right here, f of t equals lambda e to the minus lambda t, where x is bigger than or equal to 0 or 0 elsewhere. Turns out that this guy right here is what is referred to as the exponential PDF. Okay? Now think about what that would look like. Let's go into the old Desmos.com. Desmos. It's beautiful math, man. So, guy can do it a bunch of different ways. I'm just going to do well, I'm going to do an A, I guess. Well, I'll do an M, so it's kind of like a mu. I don't really care. Times E. Excuse me. E to the M times X. Nice. Make a slider for it. That's cool. Oh, this is supposed to be negative in there, you dope. Nice. And of course, what happens if you change your M? Changes the shape, yes? Obviously, the M can never be 0. I mean, negative, so it has to be bigger than or equal to 0, right? So there I am. It's going to look like this. You're like, well, what about this negative side of things? Well, I don't care. Negative didn't really happen. You with me? It starts at 0 and goes that way. Okay. Well, interestingly enough, you're like, well, that's cool. So what would the antiderivative of that be? Well, the antiderivative is 1 minus. We already know what this is. 1 minus E to the negative M X. Oh, that's nice. And then what happens, friends? We start at 0, and we build probability. We build probability until we get up here to just about 1. Are you with me? Nice. And so the green one is the CDF. So it turns out that when you do this thing here, the probability they get more than 0 things to happen is actually equal to this guy right here. This piece right in here is the CDF for the exponential distribution. Exponential distribution. And that is 1 minus e to the minus lambda t. It's the CDF for this guy. And it comes about because of this relationship right here. Okay. Now, that's where the two come together. They are two sides of the same coin. Are you interested in how long you have to wait? Or do you want to know how many do you expect to see in a certain amount of time? Okay. And it really depends, right? Like, I don't know, let's say you're, well, here you go. So you're back in the good old days when you guy could go out to a restaurant or something or a bar or what have you and whatever, and you're sitting there and you're like, I'm going to, by God, keep track of how long it is between I see, you know, some pretty lady come in the door. All right. And maybe normally it's your watering hole. It's 1 every 15 minutes. Good for you. All right, whatever. There they are. I don't know why you're down there every day. 1 every 15 minutes, you think you should go find one, but whatever. I'm just saying. I'm not judging. I'm just saying. Anywho, here they are coming in the door, and you expect to say 1 every 15 minutes. If you prefer 4 an hour, great. And then some nights in there, you're like, golly, we're waiting a long time. That's right, because you're talking about, you know, whatever reason, there's a long time between intervals tonight. You know, whatever it is, dude. I don't know. Lots of different things. Job offers. It could be a variety of things. I don't get a lot of job offers, you know what I'm saying? So maybe just, you know, do this other thing. That was kind of fakey anyways, too. But the idea of seeing, you know, where those things come out is all we're talking about. So sometimes we're interested in how many things are going to happen. That is a discrete distribution, okay? Almost assuredly. How many wins, how many losses, how many dogs, how many this, how many that. That is important. And sometimes it's more important than anything else. Other times we're talking about wait times. That we're going to be talking about, you know, time. Time is probably the most important thing that's continuous in my daily life. Just happens to be that way. And so there will always be a tie-in, okay? And I want that to be as clear as I can. Now, that said, exponential distributions, we don't use a ton of them in our daily lives. I don't personally. I use a lot of normal distributions. I mean, a ton of them. I use T's and chi-squares and F's to do interesting things with. I don't use them just in and of themselves. I do some interesting things with them. And then I use some discrete distributions. Exponential is not one that I use very often. But sometimes, you know, it's very useful for certain things. And again, we're going to try to bring up some applications as we get a little further into this deal.
That's all, folks.